In this video, I hope to demonstrate exactly how powerful this new shortcut is that we've learned. What we're going to do now is we're going to generate several different power series using that same geometric series formula. Remember that we know that the sum from n equals 0 to infinity of a times r to the n is equal to a over 1 minus r, provided that the absolute value of r is less than 1. Okay, that's the old school geometric series formula that we all know and love. Okay, so we're going to try to start with this f of x equals 1 over 1 plus x. So it should be pretty clear, just comparing these two fractions, that a equals the numerator is 1. And we've got these 1's that match up, but that's important. And then this minus r, well, if we're subtracting something, we're subtracting, well, you guessed it, double negatives is going to make that positive. R equals negative x. So we know that this is a power series where a equals 1, so n equals 0 to infinity of, I'm not going to worry about writing the 1, I'm just going to write r raised to the n, where r is negative x. So we know that 1 over 1 plus x converges to this power series, or vice versa, rather. This power series converges to 1 over 1 plus x, provided that the absolute value of r is less than 1. Well, the absolute value of r is the same thing as the absolute value of x, right? Whether it's positive or negative, I don't really care. And we're done. Unless we wanted to actually read the instructions, probably that's a good idea. Include the first four terms and the non-zero, and the general term. So we know that f of x is equal to 1 over 1 plus x, which is equal to, well, when n equals 0, we get 1. When n equals 1, we've got negative x, right? Because of a negative, this is going to be an alternating series. N equals 2 will give us a positive x squared. N equals 3 will give us a negative x cubed. And we'll get plus, minus, etc. until we get to our nth term. And we're going to continue to add forever and ever and ever, provided that the absolute value of x is less than 1. We know that these two guys are exactly the same. And that's it. We're done. Okay. Example 4, same idea, except notice that the numerator isn't 1. I want you to imagine what would happen if we tried to build this the old school way. Remember that when we did this problem up here in the orange, where we took this function and we took repeated derivatives, we could use the power rule because the numerator was a constant. The numerator is not a constant in example 4, so we can't use that trick. We're going to have to use the quotient rule. And the quotient rule is long and tedious. Forget about the quotient rule. I think that we might have seen somewhere before that the sum from n equals 0 to infinity of a times r to the n is equal to a over 1 minus r, provided that the absolute value of r is less than 1. And if our function is x over 1 plus x, which is the same thing as x over 1 minus, I like to see the minus, just like we have here, minus a negative x, then it should be pretty clear that the a value that we're dealing with is the numerator of x. And the r value is the same as it was up here. It's still negative x. So we know that x over 1 plus x is equal to the sum from n equals 0 to infinity of a, which is no longer 1, it is now x, times negative x raised to the n. Okay. So that just means that I'm going to take all of these same terms that we got up here and multiply each one of these by x. So 1 times x is x, negative x times x is negative x squared, etc. So we'll just build that series. And I don't need to write the nth term in this expansion because I have the nth term written in the summation notation. Now, when is this true? Well, this is true provided that the absolute value of r, which is the same thing as the absolute value of x, is less than 1. That's the domain that both of these match at. And that's it. We're done. See how fast this is? We've done 2 in less than 5 minutes. Let's do a third one. Example 5 here is going to use this little known fact that if we take the sum from n equals 0 to infinity of a times r to the n, we know that this infinite series converges to this fraction a over 1 minus r, provided that the absolute value of r is less than 1. It's not little known. It's very commonly known, especially to you guys, because I've said it 3 times in one video. This time we've got 1 over 1 minus x squared as my function. And it should be clear in this case that we've got a is 1. And this time r is not x, r is not negative x, r is just x squared. All right, so this means that we have the sum from n equals 0 to infinity of a times r to the n, or 1 times x squared to the n. If you would rather write that, I would, because I like it better. When you can avoid a parentheses, why not? X squared raised to the n is the same as x to the 2n, and that's a little bit nicer. And that's equal to x to the 0 plus x to the 2 plus x to the 4 plus x to the 6th plus dot 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 forever, provided that the absolute value of r is less than 1. Well, if you take the square root of 1, you get 1. So this is still the same interval of convergence. Notice another thing, I haven't mentioned this yet, but another thing that's really nice about this is we don't have to check the endpoints for convergence either, because we don't have to check the endpoints for any geometric series. If r equals 1, it's going to diverge. So this is a super quick way of generating a power series and finding the interval of convergence all in one fell swoop.